Welcome to week 3 Q&A for Organic 2. We're going to go over some of the multiple choice questions from exam 1, and then we'll also go over some multiple choice questions from quiz 3. You do have exam 2 coming up this following week for week 4, and that'll be on Thursday, and you also have a quiz 4. So we'll go over the exam. It's important because you're going to have a cumulative final exam in this class. So it'll cover Organic 1 and 2. And then the other thing I'd like to go over is your POGIL activities and talking about aromaticity. So we're going to do POGIL 19, POGIL 20A and 20B. I want to go over those mechanisms because you're going to see those in your exam 2, in your quiz. All right, so let's look. For exam 1, I picked out the questions that people scored 50% or less. And sometimes you might want to treat these questions as an open response before you click the answer. This first question talks about the acidic proton. And you have, I'll just show you the different ones in the compound here. This is a typical question you're going to see on your final. And it's really a review question. So we had some review in Organic 1. Sometimes review is a little bit harder for exams for students to do well because it's such a broad amount of material. But you should have done a lot of review in your sapling homework. But I do hope that the next quiz exam questions will be a little easier for you to score higher. So I'm trying to draw this big molecule here. And so let's look. So you're supposed to choose the proton with the lowest pKa value. So hopefully you understand that the lowest pKa value means your most acidic proton. And so if you go back to all your chapter 3, talking about the different protons and which ones are acidic, you can apply your principles. So here's HC, here's HD, here's HB, and here's HA. Now, HC is on an sp3 carbon, but it's also benzylic. But that sp3 carbon, those typically have pKa's around 50. Okay, so that's a pretty high pKa. You're looking at HD here. It's also on a carbon, and that is also an sp3 carbon. You don't know this yet, but it's also an alpha carbon, but you do have an OH. But it's going to have, as far as you can see, you could just say that's an sp3 carbon. You could say that's 50. HB is on an oxygen. Okay, so it's on oxygen. And that is a electronegative atom. So it pulls electrons towards the oxygen. And so if you were to make a conjugate base of this, which would be O negative here, that would be very stabilized. And so HB would have a pKa anywhere from 16 to 18. So that's our lowest so far. And then HA, you can look on an amide, and amide hydrogens are not acidic. Okay, so they're not acidic at all. And so that pKa, I would guess, would be around 25. So this HB should have been your answer there. And that is correct. Okay. We also had question 9. This is also another review question. Question 9 was hybridization. Hybridization. So if you need to go back and follow up on some review on these topics, then you need to do that for your final. So what is the hybridization of your oxygen atom in the structure below? So I will draw just a portion of this molecule. Now, so it's nice to put in your lone pairs, and you can see that you can draw a resonance structure here. So if you can draw a resonance structure, for this molecule, then you would see that that would have to be an sp2 carbon. So your answer there is sp2. All right, now we got to go to question number 10. Okay, this is also a review, and it was on your chapters on alkynes. Okay, so what is the required reagent or reagents in the following reaction? And you're basically going from an alkyne to, what is this functional group? It is an enol. Okay, and you know the enols then go tautomerization. So this would not be what you would actually find. You would find that this double bond picks up this hydrogen, and those electrons go there, and then you have an aldehyde. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Make sure we draw, count your carbons. Okay, so that tautomerizes to an aldehyde. So how do you go from an alkyne to an aldehyde? And that is your isoamyl boron, and then you treat it with sodium hydroxide and hydrogen peroxide. This was also a reagent that you needed in your open response. Diisoamyl boron has 5 carbons, 1, 2, 3, 4, 5, and it is slightly hindered. The other ones, you can look at those reagents, and one of them is mercury sulfate and sulfuric acid. That would give you a ketone after tautomerization. And mercury acetate is good for alkenes, not alkynes. Same thing with sulfuric acid and heat. Those are reagents for alkenes. So review your alkenes and your alkynes. Okay, so our next question. Now I'm just picking through the questions that people seem to miss 50% or more. Okay, so this is was new chapter, and it was epoxide opening. So the compound you're trying to make is this alcohol. 1, 2, 3, 1, 2, 3. Okay, so you're trying to make this alcohol, and it's asking for the starting material, and you have the reagents here. You're adding a Grignard, and then you're treating it with sulfuric or just regular acid. Now, the key here is to see that this bond is the new bond being made, and so where is that? That's this bond here. So this is your new bond. Okay, this is your new bond. And so you can see that the OH here is 1 carbon removed. So it's 1 carbon removed from that carbon. So this must be an epoxide opening. So then you would say my starting material therefore must be this here, and and then you have your OH here. So this would be your starting material, and you can see that your other materials would have put the OH on this red carbon here. But now we can see that your Grignard would attack from the least hindered side because it's basic, and you did have a POGIL exercise about that, and that does an epoxide opening, and then upon protonation, you get your alcohol. So that is how you look at that. Our next question, let's see. Which reagent transforms this transformation? That was a mistake on my behalf, and so I gave that to everyone. And I sent out something on that one. Okay. This one here is a Diels-Alder. So we didn't have a quiz on your Diels-Alder reaction. We did have a POGIL exercise. If you turned in your POGIL early, then you would have gotten feedback. So on your POGIL, you have to have a diene and a dienophile. And so you can recognize that this is your dienophile and this is your diene. And your diene's written like this. But what you're going to have to do is you're going to have to, sometimes you might have to turn it around. So you could go ahead and turn this around here and say this is 1, 2, 3, 4, 5, 6. So you're going to get a 1, 2, 3, 4, 5, 6. Okay, so this is your 5, and there's your 6. There's your 1, 2, 3, 4. And then here you have the CH3 at 2. And then you have this bridgehead here. And you have 2 of them. So there's this and this. Okay, so you have that. Now let's look at your electrons. So this electron goes to 1, 2. That goes to 3, 4. And then this goes to 5. And so you get that one here. This one between 6 and 1 became your new bond. And then you also have your 4 and 5 as your new bond. Now you also have CN here. Now if you look through there, you can see that and that drawn. This is how it's drawn in your problem, right? So here you have this. This is flat, CH3. And then you have this. Now, is this the correct answer? And you see that the substituents here are between 1, 2, and 3. And you learn that a 1, 3 doesn't happen. So what you need to do then, because this is problem solving, folks. And problem solving means you have to redraw these to get them correctly. Okay, so here if we do this one, so you see how I turned up my dienophile upside down? And so then if you draw your 6-membered ring with your bridge, then you have your CN here. And you know that CN is supposed to be endo. Okay, so that's endo. And then you have this new bond here. Okay, now these substituents are 1, 2, 3, 4. So this is the actual product, not this one, not a 1, 3. And it's also not with the CN, the nitrile going above. So I can draw that as well. And you needed to work all your problems to know the difference between this. This is one that's not correct because this CN is an XO. And you don't get an XO. So that was the Diels-Alder reaction. Let's see, our next one, we have 2 more to work on your exam. And it was a reaction sequence. You need to get familiar with doing reaction sequences. You're going to see these in your final and on all of your questions. And your best bet is to work out each reaction sequence to see what you would get. Now, we're going from an alkyne here to an alcohol. And remember, when you see an alcohol, you need to classify it. So this is a tertiary alcohol. So what carbons in this product come from the starting material? So you have 1, 2, 3, 4. 1, 2, 3, 4. So these are your carbons, 1, 2, 3, 4. 1, 2, 3, 4. All right. So those carbons came from the alkyne. So if you want to do kind of a retrosynthesis analysis, you would say this was a new bond that was broken. And then you had somehow this came from, how would you get an alcohol from here? Quite possibly a ketone. So if this is negative, how would you get this negative and this positive? This could be a Grignard, right? And there you have a ketone. And you've learned that ketones and Grignards make tertiary alcohols. That's what this is. So there's something to think about. Now, how would you get a ketone from the alkyne? Well, you know that you can do mercury sulfate and sulfuric acid, and you get the enol here that does a tautomerization to a ketone. So if you look at that, the first thing you see is the mercury sulfate and sulfuric acid. And then the second thing is the phenyl magnesium bromide. And then you treat it with sulfuric or just regular acid. And that combination would get you that. If you did the borane, that would give you an aldehyde. Okay, so that would give you an aldehyde here, folks. And aldehyde is going to give you a secondary alcohol product. Here you had a tertiary. Lithium aluminum hydride would not reduce the alkyne, so it would do absolutely nothing. MCPBA would probably make a diol of some sort, and so that's not going to work. All right, and then one last question on exam 1 to go over, and this was all new material, and this was an epoxide opening. So looking at the epoxide opening on this exam, well, you see an epoxide, and epoxides, what do? They open. So when I see an epoxide, I'm like, wow, that's an epoxide opening reaction. So here we have H3O plus and methanol. So the key here is to know that this is under acidic conditions. And the first thing that happens under acidic conditions is that your epoxide is going to get protonated. So when this gets protonated, and the hydrogen adds the oxygen, that makes an oxygen positive. Now, that means you're going to have to put a delta positive on the more substituted carbon, because this is going to be electronically driven, and now your nucleophile will come in and attack that carbon from the more substituted side. So this is the opposite of a basic epoxide opening. So then we have this here, this carbon now has the OCH3. We can keep the hydrogen there if you want to do that. And then the epoxide has opened. Now you want to regenerate your catalyst. So it's going to do a deprotonation, and then your product will be this methyl ether alcohol. And so now we need to look for those, and you can find that as the correct answer. Okay, so those are your quiz, your exam 1. Let's go over your quiz that you just took. So quiz 3. So let me find your quiz 3. Let's see, hold on. Quiz 3 right here. All right, so you had 5 multiple choice questions. So one of the questions for quiz 3 was, which of the following statements is correct regarding the classification of the following compounds as either aromatic, anti-aromatic, or non-aromatic? Now, I noticed that I got probably 17, I don't know, probably 15 Pogles in yesterday or Thursday. So the problem with that is if you would have turned it in on Monday, then you would have had the feedback before you took the quiz assessment. Okay? So you're going to have this feedback, which is going to help you for your exam too. So you're going to see this on exam 2. So you're going to have the feedback, but you lost the opportunity to have the feedback before the quiz. So I do set the deadlines on Thursdays because we have to have deadlines. If I don't set deadlines, people will not turn their stuff in. Okay? So we have deadlines, but that doesn't mean that you have to wait till the deadline. So usually my A students are getting these in on Sunday and Monday. I'm turning these back to them with the feedback before the quiz. So then they can just say, oh my gosh, this quiz is so easy, and they have the feedback. You're going to do it anyway, so if you do it 3 days before, you're going to get more points. You're going to get literally 1 or 2 letter grade higher, okay? Doesn't matter to me. I'm going to grade it just the same. It's going to take the same amount of time for me to grade it. I don't mind giving you back POGL feedback. It's not like, you know, the quizzes where I don't get release them unless we're all releasing them at the same time, or the exams. I want those all done at the same time because I want to give you feedback at the same time. POGLs is different. POGL is participation. It's your feedback. Okay, so going forward, you have 3 more weeks in this course, and you have a lot of quizzes and you have a lot of exams. So in order to do this well, I would say get those POGLs turned in. So anyway, and we will go over the POGLs talking about the aromatic, anti-aromatic, and non-aromatic. All right, so here, the first compound, um, so you just want to look at each one of these and classify them before you even read the questions and the answers, okay? Just so what is 1? Well, 1 is is it all sp2 carbons? Okay, that's the one thing you have to know. And so that's conjugated. So you had to know that this positive here, this positive carbon, is an sp2 carbon. So they're all sp2 carbons, so it's all conjugated. That would mean this is flat, okay? So this would mean that it's either aromatic or it's going to be anti-aromatic. So we got to do the Hughes rule. And so this only has 1, 2, 3, 4 pi electrons. Okay, so that's going to be anti-aromatic. Now you go to problem number 2, and these are all sp2 carbons. Okay, so it's conjugated, and you have 1, 2, 3, 4, 5, 6. So you have 6 pi electrons. So folks, that's going to be aromatic. Okay, so 2 is aromatic. Let's go to the next one. This one is going to be non-aromatic, and you have to explain why. Well, this carbon right here has 2 hydrogens, and that means it's sp3 hybridized. So it's not conjugated. And if it's not conjugated, then it's non-aromatic. So that's number 3. Let's look at 4. Now, number 4, everything is conjugated. These electrons can do resonance. So if you were to do a resonance structure here, you could see that those electrons can participate in this ring. Every one of these atoms are sp2 hybridized, And we do count this electron pair as one of the pi electrons. And you did do some problems on this in your POGIL when to count those pi electrons. If there's not a double bond to this heteroatom, then count one of those electrons. Okay, so we're going to count those as 2. And then you have 3, 4, 5, 6. And you know 6 pi electrons follows Hughes' rule, and that's aromatic. So 4 is aromatic. Let's highlight these with a little highlighter. So 2 is aromatic, and 4 is aromatic. 3 is non-aromatic, and we have 1 is anti-aromatic. Now we can read our question. Compounds 2 and 4 are aromatic. Yes. Compound 1 is anti-aromatic. Yes. And compound 3 is non-aromatic. So that is the correct answer. Okay, question number 2. You have to fill in the missing reagents. So what is the best reagent to accomplish this transformation? You're going from a benzene ring, and you're putting the chlorine on it. Okay, so you're going from benzene to chlorobenzene, and if you did your POGIL, you would know that that reagent is Cl and aluminum trichloride, and that generates a Cl plus electrophile. And then let's just go ahead and do the mechanism, because on the open response, and you're going to have to do the mechanism. So I expect 1 for you to show your electrophile. You don't have to draw how to get that, but in class I'd want you to just, with these reagents, show your electrophile, show this pi bond going after that electrophile. You always draw your electron flow arrows from nucleophile to electrophile. I want to see your sigma complex. Okay, so this is a sigma complex. And sometimes I'll ask for resonance structures. So if you were to do resonance structures, you would show that these electrons will go towards the positive, and I would just want you to show them one at a time. You draw all your bonds in here, and now your positive charge is over here on this carbon, and then you have another resonance structure here where the electrons go towards that carbon, and then those are your resonance structures. And then you can just pick one of these, and I want a separate step, and I took off points on people's POGILs because I want separate steps. When you start putting 2 or 4 electron flow arrows in there, you're telling a story, and it's not a right story. Okay, we use punctuation, we use capital letters, we learn how to write sentences when we say Jane goes to the store. When you're drawing electron flow arrows and these reaction mechanisms, you are telling a story. Okay, and every organic chemist in the world speaks that same language. Okay, so whether I'm speaking English right now, when I start drawing these electron flow arrows, if you're in Russia, they know what you're talking about. Okay, so when you have 2 steps in one reaction mechanism, you're telling a story that doesn't make any sense. You might as well just be speaking gibberish. Okay, so that's why you break it up. So here we have this, and now this is going to do rearomatization. So you can even write that on there so we understand each other. And so those electrons will go and take this hydrogen, and that hydrogen pairs will go towards that carbocation of the sigma complex. And reatomization is a highly energy favorable reaction mechanism that will happen. Okay, it's like sleigh riding downhill. It really will go. All right, so that's the mechanism, and those are your reagents. Let's go on to the next question. Okay, once again, you're going to have to do reaction sequence. Okay, so we're starting with benzene. And we're going to make this compound, and this compound is called aniline. Okay, so it's called aniline. Now, how do you make that reagent? the first thing you don't know how, there's only so many reactions you know how to do. Let's think about this. You know how to put chlorine on there. Okay, so you use a Lewis acid with chlorine, that'll give you the that ion. Okay, you have these in your Pogel, or you could do bromine, right? So you could do bromine. You could use iron bromide, and that'll put bromine on there. You also know how to do sulfuric acid and sulfur trioxide, and that's going to put an SO3 hydrogen on there. You know how to do Friedel's Craft, alkylation and acylation. That's going to make carbon-carbon. But you also know how to do sulfuric acid and nitric acid, and that gives you a nitro. And so now, if you do that, you have a NO2, and you've learned that you can reduce that using zinc, mercury, and HCl, and that nitro will get reduced to aniline. So you need this reagent here, and then you need to reduce it. So sometimes you're going to have to do multi-steps. Okay, the reaction product. So if we want to do this product, we have benzene and one, two, do we have that right? 1, 2, 3, 4. Always count your carbons. 1, 2, 3, 4. And then we have a Lewis acid. Now, a lot of people miss these, okay? So what you're not doing here is you're not doing your carbocation rearrangements on the Friedel-Crafts. So when you're doing Friedel-Crafts, alkylation, folks, and you miss this on your open response, don't miss it on your exam too, you got to look for that rearrangement. Okay, so when you make a carbocation, in any reaction you make a carbocation, you've got to make your most stable carbocation. So you will get rearrangement if you can. So you look to your neighbor, it has one hydrogen, you classify this. This is a primary carbocation. Okay, so its neighbor, if you did a hydride shift, and you have to show your hydride shift for points when I give you an open response. So if you have your hydride shift here, now the hydrogen has gone to this carbon, and now you have the carbocation on this carbon. What is that? That is a tertiary carbocation. You know that a tertiary carbocation is more stable than a primary. So now we have this benzene that would attack that, and I will show you your reaction mechanism that I expect you to draw. And I am not going to draw in your bunch of resonance structures for time, but you have your carbocation there, and just double check. So we have 1, 2, 3, 4. 1, 2, 3, 4. Okay, so sometimes you got to be extra careful to see that this is the bond you're making. And now we want to re-atomization, so I just do the Lewis base, and it's going to take this hydrogen here. Those electrons are going to go towards that sigma complex carbocation, and you re-atomize, and there you have it. So that is one of your options, and that's the correct option. And I also went through the mechanism here. Okay, you have one last question on this multiple choice section of your quiz. Which reaction sequence would accomplish this transformation? So we're going from benzene to an alkyl group. So this is going to be Friedel's Craft. And the question is it alkylation? I'm going to tell you your best bet is to do acylation plus reduction. And why is that? Well, if you did retrosynthesis analysis, you would break this bond right here. You would say, okay, here's my starting material, the benzene, very good. And then you would say, okay, this is my added carbons here, And then you'd say, okay, let me add a Cl there and aluminum trichloride. Okay, well, what does this give you? It gives you this carbocation. You classify that carbocation as a primary. Yes, you will have a hydride shift. It's what we just did, folks. Okay, so what would you actually get if you did this? You would get this compound here. As you can see, this compound is not this compound. So that means you need to do acylation and reduction. You had some questions in your POGL. So if you did your POGL early, you would have seen that. So the best way to do this is to do benzene, and Friedel's Craft acylation would be where this is actually an acid chloride and then aluminum trichloride. So when you do that, then you get the acylium ion. So you would get this, and then that would add. So now you would get this compound here, and then you can reduce it just the same way that you reduced the nitro to the aniline. You can add zinc, mercury, and a solution of sulfuric acid, and you will just remove that oxygen and you will replace it with hydrogen. So we call that decarbonylation. And it is a reduction. It's called decarbonylation. Whenever you put DE in front of a word, that typically means to remove. So then we look at that, and I see that we have CH3 to CHCOCl, and that is this reagent, folks. CH3, CHCOCl. Okay, so that takes care of the sapling multiple choice questions. Now I want to touch on your POGL for the week. After going through there, I have given everybody feedback, but let's just touch over it just for an overview. Okay, so when I look at your POGL 19, most people might have lost points because they didn't explain. I expect everything on your POGL. I expect those structures. Okay, so let's just look at these real quick and we'll go over them. So the first one you're supposed to classify is aromatic, non-aromatic. And so a lot of people got this right. They said, oh, it's non-aromatic, but that wasn't okay enough. You had to say that these carbons here are sp3 carbon, which means it's not conjugated. Okay, and that's what makes it non-aromatic. The next one, you had this compound here. And so if you look, every atom here is sp2. Just go walk through. Okay, so these are all sp2. So everything's sp2. So the question is, I mean, it's flat, it's planar, it's conjugated, sp2 atoms. So is it aromatic or non-aromatic? So now we've got to count the pi electrons. Now, we count these, 1, 2, 3, 4, 5, 6. Do we count the lone pairs? No, we don't count the lone pairs because on this nitrogen you have a double bond. So no, we're not going to count, not count. This nitrogen here also has a double bond, so we're not going to count. Okay, so then we only have 6 pi electrons. 6 pi electrons does follow Huckel's rule. That one is aromatic. All right, so for this one here, we have, and when you don't have the lone pairs drawn in, you better draw them in. Okay, so here we have this is an sp3 carbon, and that means it's not conjugated. And if it's not conjugated, you just go ahead and say it's non-aromatic. Okay, it's not aromatic. Okay, let's go to the next one. We have a double bond there, we have a double bond here, we have a double bond there. All right, so are each of these atoms sp2? This would be sp2. because those electrons could go and do resonance. Okay. And then this is sp2, 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 sp2. So they're all sp2. So they are all conjugated. So now is it aromatic or anti-aromatic? You count pi electrons, 1, 2, 3, 4, 5, 6, and you're going to count this lone pair. So you have 8 pi electrons. You can also look and say, does that oxygen have a double bond to it? No double bond. Okay, so no double bond. So yes, count one of the lone pair. So you got to count that lone pair. And that also shows you that it does do resonance. And so that would put those electrons there. And there you go. So that would be a resonance structure. And those lone pairs do participate in resonance. So this is going with 8 pi electrons. You got anti-aromatic, folks. All right, and the next one here is all right. So first thing you want to do is find out is every atom every atom sp2. That's sp2, sp2. This is going to be sp2 because those electrons can participate in resonance, and I will draw that. So there's those electrons there. Okay, so, and this is sp2, sp2. This nitrogen, you can see that this nitrogen is sp2, so what does that look like? So if those electrons went here, and those went there. Okay, so those can participate too. So every atom's sp2. And the question is this aromatic or non-aromatic? You're going to have to count your pi electrons. You would count 1, 2, 3, 4. You have to count one lone pair. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 pi electrons. And so one of the ways you can do this is when you look at the structure, does this oxygen have a double bond to it? No, so you must count. Does this nitrogen have a double bond to it? No, so you must count those lone pairs. 8 pi electrons, that's anti-aromatic. Okay, some people miss that. The next goal was just to show you the Diels-Alder and how it does decarbonylation. The driving force is to make an aromatic compound. Okay, let's go on to 20A. So 20A on your POGL. So 20A, I expected you to draw these reactions out with benzene. And I'm not going to draw every one of them out, but when you draw the sulfuric acid and the nitric acid, I expect you to show your electrophile, and I expect to see this for your open response on your exam and on your quizzes, so this is what I expect to see. And I actually want to see your nitro Lewis structures. So what does nitro look like? This is what nitro looks like. Okay, and this is your sigma complex. It'd be nice if you write sigma complex. And then sometimes I might ask for resonance structures, and other times I'm not. I didn't ask for resonance structures on this. And then you need to do reaerodization. Sometimes you can just choose something here, but I need to see that you're subtracting this hydrogen and it's going towards that ring to reestablish aromaticity. And then you have your nitro. Okay. Br2 and FeBr3. Then I want to see the Br plus, and then everybody seemed to get the answers right, and that wasn't a problem. But the problem the people had was, one, they just wrote the answer. I don't care about just the answer. I want to see, what is your strong electrophile? I want to see, what does that sigma complex look like? Okay. I want to see those electron flow arrows going from benzene to that carbon to make this sigma complex. I want to see the re-aromatization reaction to see if you can draw your electron flow arrows properly and attacking the correct hydrogen. Okay, so the other one, 13, so you can do all of those. I feel confident that you can. When it says explain, I want you to show the problem with this reaction. I want to see that product. I want to see your carbocation rearrangement. I want to see the hydride shift. I want you to write hydride shift. And I want to see that reaction mechanism. And so you can go ahead and draw all of that out and the reaction mechanism. All right, 20B. 20B is your last POGIL in this Q&A, and I did want to see resonance structures for one of the electron donating groups, and I wanted to see electron withdrawing groups. So I will take my time and go through these because this one's important. So let's look at the first one, and the first one is aniline. And your reagents are bromine and iron 3 bromide. Now, the important thing here, all you have to do is show me Br plus. You don't actually have to show how that is generated. Now, the way I do it, and some people threw those electron pairs in the ring, because the nitrogen does have these lone pairs, this is going to be ortho or para, and you can just draw one of these. You didn't even have to draw both, but a lot of people drew both, and that's fine. On the exam, I just want to see one, and I just take the one here and put the bromine on my ortho position. You still have your hydrogen, and I want to see that sigma complex. Now I wanted to see resonance structures. So resonance structures here would be this lone pair going, or pi bond going towards that sigma complex. And you can draw everything else in. You can draw your bromine, your hydrogen, and now you have the carbocation on this carbon. And you can draw this, and you see how I take my time and draw one electron flow arrow towards that positive carbocation. We learned that in Organic 1, that when you have a carbocation, you draw those electron flow arrows towards that carbocation. Now we have these electrons that are going to go, the lone pair, that are going to go towards that carbocation. And this is important here. This is your most important structure. And the reason why, it explains, this one right here, explains why this is an activator. An activator means it's going to be a lot faster reacting than benzene. And it's because these lone pairs can go into the ring and the positive charge is stabilized on the nitrogen. And that's a more electronegative atom than carbon. So this is going to be very activating. And then you need to show one of these, and you'd have to redraw, okay, because I've already got these electron flow arrows, so I want you to break it up into a single step. because you're telling a story to show the reatomization. So then you could show this iron with 4 bromides that give it a negative charge. You could show how this will abstract this hydrogen to do rearomatization. And then that gives you your product. And so you got bromine, and you didn't have to show all of them. You could just show an ortho or para. I don't want both ortho and para on the same molecule. All right, let's do the next one. The next one is electron donating, and it's a Friedel-Crafts acylation. And so that's going to generate the acylium ion. And then you can show, so if this is an electron donating group, the alkyl group, you can do ortho or para. This is probably going to go para more so just because it's sterically hindered. You can show your sigma complex. And so this is the para position. Okay, so there's my para position. So there's my sigma complex, and you could write that out. You're telling your story, and then you can show reatomization. Aluminum tetrafluoride would take this hydrogen, those electrons would go there. This would be reatomization. And there we have the Friedel-Crafts acylation product. And you can write on there rearomatization. Now, if you wanted to draw your resin structures here, I would recommend that you just start with your sigma complex. And you can go from there. So those electrons would push towards that sigma carbocation. And this would put the positive charge there. Those electrons would go here. And what I want to point out here is that alkyl groups are activating. That means the reaction's happening faster than benzene, and they're going to be ortho-para directors. Well, let me just show you why. It's because of this compound right here, this intermediate. Do you see how you have your carbocation on the tertiary carbon? Okay, you can't get a tertiary carbocation in benzene, but you can when you have an alkyl group, and that makes it activating. The next one we have is a nitro. So nitro here, and I wanted to see the nitro drawn out. So I want to see your Lewis structure of your nitro. So when you're drawing out reaction mechanisms, all of your formal charges and lone pairs and everything matter. Now you see nitrogen has a positive charge. This is the first time we've seen electron withdrawing group, which is going to be a meta director. So when we have this here and we get the electrophile chlorine, then we're going to go here to the meta. So this is going to add there. You can show your sigma complex. I would like for you to practice drawing these structures as much as possible. So you put chlorine here. And so there's your sigma complex. And then you can show reatomization, where this comes here and takes that. And now you have your chlorinated meta nitro compound. Now, let's look at resonance structures here. You might want to redraw your sigma complex. And You push your electrons here, and then you redraw. Now you have your positive charge here. You redraw. Electrons go towards there. And then your carbocations there. So that's all your resonance structures. Now, this is a deactivator. This is so slow compared to benzene, okay? Deactivator. And the reason why is because nitrogen has a positive charge, and there's nothing particular here. I mean, you got your carbocation on a secondary carbon, secondary carbon, secondary carbon. The reason why it's a meta director, meaning your electrophile is going to add at the 3 position, is because it avoids a positive charge on the carbon bonded to the nitrogen. You don't want a positive positive. Okay, you can see that in your slides in this chapter. A positive positive right on top of each other repels each other. That's a law in physics. You don't want positive and positive right next to each other. The last reaction shows 2 substituents. So you have a CH3 and then you have an OCH3. And then your reagents are sulfur trioxide and sulfuric acid. And you know that this is your electrophile here, this sulfur trioxide. We call this fuming sulfuric acid. Now, where does it go? Well, this is an activator. So that's your alkyl group. And then you also have oxygen, which is an activator. And the oxygen is going to be more activating because the oxygen has a lone pair. That's going to be about 10,000 times faster of an activator than benzene itself. So that means that your sulfur trioxide can either add ortho to this, the more dominant. So you can add ortho, or it can add para. And either way, that's going to put the substituent meta to this CH3 group, but because this is so activating, it will happen. So all you had to do was you could just choose one or the other. So when you do this here, and then that also picks up a hydrogen there. All right. All right, well, that covers your POGL activities for week 3. And week 4, we're going to start talking about, let's look at week 4 and see what we have. Week 4, we're going to start talking about chapter 21. So for your exam 2 coming up on Thursday, it will be over chapters 16, 17, and 18. And so 18 is POGL 21, and it's talking about aldehydes and ketones. And you have a quiz on Monday. So I would recommend you go ahead this weekend and work those POGLs and hopefully turn them in within 24 hours before you get feedback. And however, your quiz on, let me just see your quiz on Monday. Let's see what it's going to cover real quick. Looking at your quiz on Monday, it's going to be, yeah, so you're still going to cover the last POGL that you had. So it's going to go, your quiz on Monday will be over these POGL questions we just worked, POGLs 19 and 20. So you're good there. All right, well, and then get POGL 21 in before your exam 2 for that feedback. And I'll do another Q&A, possibly um, Tuesday or Wednesday, possibly Wednesday. I will start, I know people like the exam wrappers. I will put up an exam wrapper for exam 3. Okay, I'm not going to do it for this exam, and the reason why I'm not going to do it for this exam is I didn't do it for the first one because we had some review for Organic 1. So um, I'm not doing it for this one because I want to see how well you can organize your lecture notes and review the material and utilize the resources that I've given you and draw your reaction mechanisms properly and use those resources that I've given you, those additional problems, and check yourself. Okay. Um, I do think exam wrappers are helpful and beneficial, but sometimes they're so specific that I think students will not utilize the other resources that I have put on there. And I don't want people taking shortcuts and essentially not going to class and not going to lectures. So let's see how people do with your POGIL exercises. Not being lazy. We're talking write out the reaction mechanism. I want to see electron flow arrows going in the correct places. I want to see correct formal charges. And so when I feel confident that the class as a whole can demonstrate that they understand functional groups and how to draw electron flow arrows, then I don't mind giving more specific resources available to you. And so I will plan on doing that for exam 3, but I'd like to see how well people can do for exam 2 with the resources that you have available to you. Okay, send me emails and questions.